Okay, guys, recording is in progress. Welcome to our class today, July 19th, 2022. The extra classes that we have during the last few weeks helped us to arrive to the last class of our course, which will give you more time to prepare your project and your final presentation next week. Then we'll give you also another 2 weeks to submit your final report and study for the final exam. Our schedule today, we will have only one session, no extra class. So I believe our class will be between 1 hour and a half till 2 hours maximum. All will be recorded for your reference, and I will upload it immediately after the class. So we will start with bias, variance, trade-off, and the problem of overfitting and the cross-validation in machine learning. Then the second video will talk about machine learning model evaluation and the evaluation metrics. So they are available in Android and G also videos. If you would prefer to watch those videos in Android and G, the 112 videos, it's there in the YouTube, or whatever you feel comfort with in the YouTube. So I would prefer to have those 2 videos today from 2 different professors. So let's start. Then we will start talking about the final presentation, the final report, and final exam. Wish you the best of luck. I'll share my screen now. Can you see my screen, guys? Thank you, everybody. I'll start playing the video.
Hello, this is Professor George Easton.
Is the sound clear?
In this video, I'm going to talk about the bias-variance trade-off, cross-validation, and overfitting in the context of prediction. So as an introduction, the situation we are considering is as follows. Suppose we have a set of data consisting of a dependent y variable and a set of x variables, just as you would have in a regular linear regression. But in this case, we're imagining that our dependent y variable could be some nonlinear function f of the set of x variables plus an error term epsilon, which plays the same role as the error term in a regular linear regression. Now let's also suppose that we have randomly divided our data into at least training and validation samples, and ideally we would have also included a final test sample as well. And finally, suppose that we have calculated on the training data an estimate of this nonlinear function f of x, which we are going to denote by f hat of x. So I want to reiterate that this x here, which I've written with a capital X, really represents a set of independent explanatory variables, just as you would have in a regular linear regression. So just to make this clear, if our f hat of x came from linear regression, then f hat of x would be equal to alpha hat plus beta hat 1 times x1 plus beta hat 2 times x2 and so on up to beta hat p times xp, where these coefficients alpha hat and beta hat 1 to beta hat p are just the usual least squares fitted regression coefficients. In this case, these fitted coefficients, the intercept alpha hat and the slope coefficients beta hat 1 to beta hat p, are going to depend on the y values and the x values in the data that they're estimated from. And so what this means in this case is that our f hat of x depends on the training data. So if I were to use a more complete and thorough notation, what I would do is represent f hat of x as being dependent on the y training data and the x training data. But this notation is cumbersome, so I'm going to suppress the dependency on the training data here. But you know now that f hat of x really depends on the training data through the estimated coefficients. Now my example here has been based on linear regression because I expect that you are very familiar with linear regression. But remember, what I'm really thinking about here is that my function f hat of x is some nonlinear function of those explanatory x variables, and that it is an attempt to estimate some true underlying nonlinear function that relates those explanatory variables to the dependent variable y. Now, before we get into the bias and variance trade-off, I want to remind you about what bias and variance are. Let's suppose that I have a statistic S. I'm just using the capital letter S here to represent some statistic, which will be computed off of data. And let's suppose that this statistic S estimates some unknown parameter theta. So again, if I want to get specific to the case of regression, then the fitted regression coefficient beta hat is going to be estimating the true slope coefficient beta. Then the bias of our statistic S is going to be the difference between the expected value of S and the value of the thing that is estimating, the theta. So the bias of S is the expected value of S minus theta. Now the variance of the statistic S is just going to be the expected value of the squared deviation of the statistic from its mean. So what that means is that it's the expected value of S minus the expected value of S, that's its mean, and take that difference and then square it, and then take the expectation of that squared difference. That is the definition of the variance of S. So now applying these definitions to our function f hat of x, the bias of f hat of x is just the expectation of f hat of x minus the true f of x that it's trying to estimate. Similarly, the variance of f hat of x, just plugging f hat of x into the definition of the variance, the variance of f hat of x is just going to be f hat of x minus its expectation. You take that difference and square it, and then you take the expectation of that squared difference. That's going to be the variance of f hat of x. So I'm now in a position to give you the formula for the bias-variance trade-off. The formula is as follows, and I'm now going to explain each of the terms. The term here on the left-hand side that we're going to decompose into three terms on the right-hand side is the expected mean square error of the prediction on the validation sample. So the mean square error of the prediction is going to be the actual realized value minus the value predicted by f hat of x, and then you square that difference and take its expectation. So this is the expected mean square error on the validation sample. It's going to be equal to the variance of the fit. So this is the formula that I just showed you for the variance of f hat of x. So it's f hat of x minus its expectation, take the difference and square it, and then take the overall expectation, plus then the squared bias. So the bias was the expectation of f hat of x minus the true value, which is f of x. And then this is squared. And then finally we add to that the variance of the error term epsilon. So this is the variance of the error, which we're going to assume as usual is sigma squared. Now I have a note here which is really mostly to myself. So y here is a new observation from the validation sample. F hat of x will be computed using the x from the validation sample, but the coefficients that define f hat of x will have been estimated from the training sample. Since the coefficients that define f hat are calculated from the previous y's that were a part of the training sample, the new observation y and the f hat of x are going to be uncorrelated. The x here used in f hat of x is the new x corresponding to this new y observation, but our analysis is conditional on this x, so it's considered a constant. Now, it's not all that difficult to derive this formula, but I'm not going to do that here because I really don't think that it's all that useful. But what is important is the idea that the prediction mean square error, so this is the mean square error of the prediction on the validation sample, is going to be equal to the squared bias of the fit, that's a bias term, plus the variance of the fit, and then finally the variance of the error. Now, this is sometimes said in kind of a shorthand way that the MSE is the bias plus the variance. And this is not quite right because it's really the bias squared, and in addition the variance of the error has been left off. But this is basically the idea, is that the major components of the prediction mean square error correspond to a bias piece plus a variance piece. Now, on the training sample, the mean square error always goes down as the model f hat of x becomes more complex or has more parameters. And this is intuitive because the more flexibility you have in fitting the data, which is really what's meant by saying that f hat of x becomes more complex, but the more flexibility you have in fitting the data, the closer you should be able to come to a perfect fit of that data. But on the validation sample, things are different. On the validation sample, what generally happens is the mean square error will usually go down as the model increases its complexity, but only up to a point. The mean square error is going down initially as you increase complexity because the bias is being reduced. But then the mean square error on the validation sample will start to go up. And it goes up because of the phenomenon of overfitting. And overfitting begins to occur when the model complexity gets sufficiently high that random features of the training data are being fit by the model. Well, this is a very important idea. And that idea is that the mean square error will initially decrease, but then increase on the validation data, even though the mean square error continues to decrease on the training data. And as I say, this is really a very important concept to understand. So now I'm going to make an illustration that shows what I've been talking about over the last few slides. So I'm going to begin with an x and a y axis. And on the x-axis, we're going to represent the complexity of the model we're fitting. And remember that complexity often corresponds to the number of parameters. And on the y-axis, we're going to put the performance of the estimator. And since we've been talking about prediction, that's going to be, in this case, the mean square error. Now, on the training data set, our models may start out performing not very well because they are not sufficiently complex to represent the structure in the data. So when the model is too simple for what's going on in the data, the model will fundamentally suffer from a substantial amount of bias, and it won't be able to perform very well. But as the model complexity goes up, on the training data, the performance will improve, and it will continue to improve as the bias is removed because the model becomes sufficiently complex to actually fit what's going on in the data. But then it will continue even further, and eventually it's going to fit the data essentially perfectly. Now, it's typically going to be able to fit the data essentially perfectly when the number of parameters is about the same as the number of data points. Well, what happens on the validation data? Well, on the validation sample, you're very likely to start in essentially the same place if you're fitting a model that is too simple for the structure in the data. Then, as the complexity increases, the performance of the model on the validation data is also going to increase. But at some point, the performance on the validation data is going to start to taper off. And this happens when the complexity of the model is sufficient that there's essentially no bias. But then as you add additional complexity, what's happening is that the model is beginning to fit random noise in the data. And as a result of that, the performance on the validation data will decline. So this trace is for the validation data. And then this trace is for the training data. So the best possible model is the one that corresponds to the minimum of the trace for the validation data. It's going to be the model that has sufficient complexity that it's able to fit the structure in the data, but not so much complexity that overfitting is beginning to occur. Now, before I go on, I want to make some comments about the problems of overfitting and of model selection in statistics. Traditionally in statistics, the sample sizes that we have been dealing with have not been so large that it's been particularly practical to hold out a validation and a test sample. As a result, the field of statistics has developed a number of goodness of fit methods that try to prevent overfitting of the data, all on the training data, and that is without a validation sample. So it's all done within sample. One example that I expect that you're familiar with is the adjusted R-squared in regular least squares linear regression. And as you probably know, the adjusted R-squared can be used to choose between regression models that have different sets of x variables. So the idea of the adjusted R-squared is that it penalizes adding in x variables that do not contribute anything to the regression. And this is different than the regular R-squared, which will continue to get better as new x variables are added into the model. So using the adjusted R-squared to try to pick the best model is intended to prevent overfitting, because the adjusted R-squared does not reward adding in variables that are not contributing in a meaningful way to the overall fit and are just fitting random noise. Now, another goodness of fit measure that is used in model selection and intended to prevent overfitting is called the AIC, which stands for the Akaike Information Criterion, and it is named after the professor that proved the main asymptotic result about this measure's behavior. But for the AIC, the smaller the value, the better. There's also a corrected version of the AIC that works better in small sample sizes, which is called the AICC. So like the adjusted R-squared, the AIC can be used to choose between models that have different sets of x variables. And I'll add here that the absolute magnitude of the AIC does not have a reasonable interpretation. So the usefulness of the AIC is to compare the values between models that have different sets of x variables. Now, the AIC and the AICC in smaller samples is probably a better method for model selection and to prevent overfitting than the adjusted R-squared. But overall, having a randomly drawn validation sample is a more direct test of overfitting. And when you do have enough data to randomly split your sample into a training set and a validation set, using the validation sample is probably better than using any of the in-sample measures. But do not interpret this to mean that these measures, such as the adjusted R-squared or the AIC or AICC, are not useful, because they are. I think they tend to be quite useful in terms of limiting the set of models that you fit on the training data set, and then you can go on to verify which one of those is best using the validation sample. So I've talked some about overfitting at this point, but now I want to address overfitting specifically. Now, when a model is fit to a data set that has sufficient flexibility. And here, flexibility and complexity really are essentially referring to the same thing. But when that model has sufficient flexibility that it begins to fit random features in the data, it's said to overfit the data. When you have such a model, the bias in the model will typically have gone down because the flexibility is allowing that model to fit the main structural features in the data. But the variance will increase because the model is actually responding to the noise in the data, and it's actually fitting the noise in the data. So now, referring back to the bias versus variance trade-off, when you are overfitting the data, the bias will be low, but the variance will be high. And referring back to our y equals f of x plus a random error model, what's happening is that the fit will be picking up the noise in those error terms, and the residuals will be unrealistically small. So we've talked a lot about the validation data set so far, and we've mentioned cross-validation in passing, but now I want to address cross-validation directly. So in statistics, methods that split the data into training and validation data sets generally go under the name of cross-validation. So what we've been doing, which is just splitting the data into a training set and a validation set, randomly of course, is a form of cross-validation. So let me just clarify a little bit the difference between the first and the second bullet here. Many of the methods that go under the name of cross-validation in statistics involve splitting the data into training and validation data sets multiple times. What we have done so far is just take our data and split it into a training and a validation and perhaps a test data set as well, but just a single time. So when we split the data into a training and validation data set randomly a single time, this is really the simplest kind of cross-validation that we might consider doing. So let me just remind you of how you generally do your splitting of data in data science. In the context of data science, you're generally thinking about very large samples, and you want to split your data into a training sample, a validation sample, and then finally a test sample. Typical percentages for the various splits might be 50% for the training sample, 25% for the validation sample, and 25% for the test sample. Or you might split it 60% for the training, 20% for the validation, and 20% for the test. If you have a relatively small number of observations, for example, say 300, you might forego the test sample and just use a 2/3, 1/3 split. So 200 observations in the training sample and 100 in the validation sample. So now how do you use these samples? Well, the training data is used to estimate or fit a relatively small set of models. So for example, these models may be several linear regressions that have different sets of x variables. Or they might be a collection of regression trees with different numbers of end nodes. Or you might compare regression trees to linear regression models. But when I say fitting, what is meant is the estimation of the parameters of these models. So for example, if one of the models is a linear regression, then calculating the fitted linear regression coefficients. That is the idea of fitting. Now, the validation data set is used for a different purpose than fitting the coefficients. What the validation data set is used for is to pick which of the models that are being considered that were fit on the training data set is the best. And in the context of prediction, best is determined by which one of those models has the smallest error in predicting the y values on the validation data set. So the validation data set is really being used to determine the right level of model complexity, or equivalently, the right level of model flexibility. Now, the real power of cross-validation is that cross-validation generally prevents overfitting the data. Why does that happen? Well, the random noise or random features that end up in the training data set that are fit by a too flexible model are not likely to also be occurring in the validation set. Different random features may occur there, but those features won't have had any influence on the model fit to the training data set. So a model that overfits the training data set will generally perform badly for the validation data. And because of this bad performance in comparison to simpler models that don't overfit, the overfitting model will not be selected by the validation data. Now, once you've decided on your model, you can then, if you want, refit the model to both the training and the validation data, which will of course increase your sample size and therefore reduce the variation in your estimates. And then if you have a test data set, it can be used as a final check. So what I've been discussing here is one of the most important and central ideas in data science. So I want to summarize it again and make sure that I've clearly stated how you think about what's going on. The training data set is used to both discover and to fit, which means to estimate the model's parameters, a reasonably small number of models. These models typically should span a reasonable range of flexibility or complexity, because exactly how much flexibility you need to fit the structure of the model without overfitting is typically not clear just by examining the training data set alone. So the deliverable, the thing you should get out of the training data set, is a reasonably small collection of models together with their fits, which means estimates of their parameters based on the training data, that can then be tested on the validation data set. These models, which were discovered and fit on the training data set, then compete on the validation data set by predicting the y variable. So what this means is that the x variables for each observation on the validation data set are plugged into these predicting functions to get a prediction for the y variable. You do not refit or re-estimate the parameters for these models on the validation data set. You just apply the models to the x variables to get predictions for the y variables. The validation data set then is used to pick the right model complexity and/or structure based on how well the models do in predicting the y values on the validation data set. So now, in conclusion, it is really hard to overstate the importance of using cross-validation in data science, and really any time that you have enough data that cross-validation is feasible. This problem of overfitting of the data is generally very much underappreciated. It's really not especially intuitive. And if you have enough data, cross-validation is easy enough to do. So you should basically always do it so that you get an out-of-sample assessment of whether or not the model that you are considering is, in fact, overfitting the data. And finally, there are other ways to do cross-validation, such as leave-one-out cross-validation or k-fold cross-validation, that I'm going to talk about elsewhere. The purpose of this video is to really clearly identify what the bias-variance trade-off is, and to discuss how cross-validation prevents this problem of overfitting. In part 2, we're going to look at an example that will give you a very clear idea of what overfitting is and how cross-validation tends to prevent overfitting from occurring.
Okay, guys, now we'll move to the evaluation matrix.
Data science, and even though I have graduated from applied informatics program at my university, it was a long time ago, and most of the practical knowledge comes from courses, pet projects, competition, that sort of thing. And one of the things that was confusing for me was evaluation metrics. Why there are so many? What's the point? What's the difference? What do they mean? And today I'm going to try to save some of the confusion to those who are relatively new to machine learning. So, what's an evaluation metric? Just a quick recap, it's a way to quantify performance of a machine learning model. And it's basically a number that tells you if it's any good, and you can use this number to compare different models. It is not the same as loss function, although it can be the same thing, but it doesn't have to be. So basically the difference is that evaluation metric is something, loss function is something that you use while you're training your model, while you're optimizing, while evaluation metric is used on an already trained machine learning model to see the result, if it's any good. And today I'm only going to focus on supervised learning metrics. We only have 40 minutes, and I'm not going to cover them all. There's a lot of them, but these, I think, are the main ones to know, to understand them, and I'm going to give you an idea of what they are and how they differ. We're going to start with classification metrics, and to make things a bit simpler, I'm going to start with a binary classification problem. And the first metric that you encounter on your machine learning journey if you're doing classification is, of course, accuracy. And it is a number of correct predictions out of total number of predictions. It's super easy to understand. It ranges from 0 to 100% or 0 to 1. And it's very intuitive. You can easily get it in scikit-learn for any classificator with a score method. So the score method for estimators in scikit-learn gives you an evaluation metric, and for classificators, it is accuracy. So I built some logistic regression on some test data, some sample data, and I get almost 96%. Well, this looks amazing, but it may not be that good. We don't really know because we don't know the context. And I'm going to show you why this is not necessarily a good thing in this case. I'm going to use the same data set to build a dummy classifier. And a dummy classifier in scikit-learn is something that doesn't learn anything from the data. It follows a simple strategy. It can generate predictions uniformly at random, or it can, in my case, just predict the most frequent value or the most frequent class it has seen in the training data. And in this case, I'm going to get 94% accuracy, and this is because the data is highly class imbalanced. I made this artificial data set with 10,000 samples, and here you can see that only 95% of the examples are positive and the 5% are negative. So simply saying that everything is positive, we're going to get 95% accuracy. In this case, 94 is probably because of the way the data got split. So 96% accuracy, is it good? We don't know. Is it a good model? Is it a bad model? If we don't know what our data looks like, we cannot say if it's a good number or not. And even if it was balanced data, we wanted to improve. From just this number, we cannot know what the errors the model is making and what to do with them and how to improve. But luckily, there is a lot of other classification metrics that we can use and diagnostic tools, and we're going to start with confusion metrics. Confusion matrix is a table, basically a matrix that gives you numbers of how many samples your model classified correctly for what they are and how many it mistook for something else. It's technically not a metric, it's more of a diagnostic tool, but it helps to get insight into the types of errors your model is making, and it also helps to understand other metrics that are derived from it. So that's why we're going to look at it. Here's another example. I built a basic random forest classifier and got 83% accuracy on it. So to understand what errors my model is making, I'm going to build a confusion matrix. And to do that, you can simply import confusion matrix from scikit-learn.matrix. And a convention is that first you pass the actual values to a metric, and then you pass the predictions, and you get this beautiful array, which if you haven't seen a confusion matrix before can leave you confused. And to understand this better, typically confusion matrices are also represented as tables, just like this one, for example. So by convention, on the rows you get the actual values, and in the columns you get the predicted values. This is the convention that is used in scikit-learn and, for example, in TensorFlow, but be careful because other tools may be using a different convention, and it's going to be the other way around. So even, for example, a Wikipedia page has it the other way around. So sometimes tutorials or articles on this can be misleading, and you need to pay attention to what's where. So we can learn a lot from this matrix. For example, on diagonal, we have the true negatives and true positives. True negatives are the values that were predicted negative and they were negative, and, well, true positives is when it was predicted positive and it was positive. We also get false negatives, false positives, and by summing up the true negatives and true positives and dividing by the total number of predictions, we can get the accuracy, but I wouldn't be showing the confusion matrix just to show another way to get the accuracy. There are other metrics that we can get from it. Let's say we're building a spam filter or a recommendation system, something for a user where if we say that this is something that you want and they don't really want it, we're going to be super annoying. If we see something, or if we put some important email in the spam folder and it's not a spam, again, users will be really pissed. So we don't want that. So we care about false positives. We don't want to say that this is the thing that you want when it's not. And in this case, one metric that it was going to be helpful for us is precision. Precision is calculated by dividing true positives by the sum of true positives and false positives. So if we don't have any false positives, this is going to be 1. And if we had some false positives and then we manage to reduce their number, we're going to improve the metric, and it's going to be a bit closer to 1. Now, another case is, for example, if we do something with medical diagnosis, and we don't want to send people home saying that they don't have a disease, but they do actually. In this case, we're caring more about false negatives. And in this case, we need recall. And it's very similar to precision, but in this case, we care about false negatives and about having as little of them as possible. And there is another way of summarizing the confusion matrix in one number, taking into account both precision and recall, and it's F1 score, which is just a harmonic mean of the two. So, depending on your business problem, you might want to care not so much about accuracy, but not only about accuracy, but also about precision if you want to minimize false positives, or recall if you want to minimize false negatives. And these are actually, unlike confusion matrix, these are actually numbers which you can compare, and you can get them easily from scikit-learn.matrix, the same way as we got the confusion matrix by passing the actuals and the predictions. And we can use them, for example, in grid search. If we want to choose a model that gives us better recall, we're going to put the scoring parameter recall. And in this case, it's going to get us the estimator that's going to give us the best recall among the possible versions of hyperparameters. Another way to summarize a confusion matrix is called Matthews correlation coefficient. And what's important to notice about this formula is that it takes into account all 4 cells of the confusion matrix. And this is important because it gives it makes it different from F1 score and has some nice properties. I'm going to show you with examples. So let's say we have this data. We have 100 of samples, 95 of them are positive, 5 are negative. And we're just going to use a dummy classifier, so we get 95% accuracy on this. Now we're going to calculate F1 score, and it's going to be even better than accuracy. It's going to be 0.97. And then MCC is going to be undefined. Scikit-learn is going to return 0 and give you a huge red warning because you're dividing by 0. And this is good because this is the only metric so far that gave you any red flag, any indication that something fishy is going on with your model. And it is because it's a dummy classifier. There's nothing good about it. Now, another example. Let's say we have the same data, but now we managed to classify one negative, so it's a little bit better. We get a F1 score of 0.9452. We get MCC of 0.135. But what we're going to do, we're going to say, OK, now what we called positive, we're going to call negative. The data is the same. It's just the way we say, like, this is a positive class, this is a negative class. We're going to use the same model, and we're basically just flipping the confusion matrix. Everything's the same, but F1 score changes for this model, and MCC doesn't. And this is precisely because F1 score takes into account true positives, false positives, and false negatives, and does not care about true negatives. So F1 score is very sensitive to what you call a positive class and what you call a negative class, while MCC is not. So far, and I feel that if you want to summarize a confusion matrix in one number for a binary problem, MCC gives you a better feeling of what's going on. But unfortunately, there's, of course, a downside. It doesn't really extend that well into a multi-class problem. And so far, we've looked only on the metrics that take into account whether prediction was correct or not. But a lot of classifiers, they generate probabilities of an example belonging to one class or the other. And there are, of course, metrics that take that into account. For example, one of the popular metrics is ROC curve, which stands for receiver operating characteristic. And to be honest, this is one of those cases where knowing what the abbreviation stands for doesn't really help to a normal person to understand what it is. And this is basically a plot where you have a false positive rate on the x and true positive rate on the y-axis. And why is it a line? Why is it a curve? Why is it not a dot? And this is where the probability thresholds come to play. When we have a probability generated of an example belonging to one class or the other, it's by default is 50%. There's a decision threshold where we decide, okay, if the probability is larger than 50%, then we're going to say it's a positive class. And you can actually change this threshold. You can move it around. You can say, okay, we are only going to say that it's a positive class if the probability is higher than 60, 70, 80. And if you move, you're going to, this threshold number of true positives and true negatives is going to change, because if something was classified as positive with 60% probability, and it was, if you move the threshold to 80%, it's going to be misclassified as false negative. So that's exactly what's going on here. We're going to be moving the threshold, and we're going to be, at each threshold, calculating the true positive rate for the model and the false positive rate, and we're going to plot it as a dot and then connect them with a curve. And the next question is if it's a good curve or a bad curve. And to me, it was helpful to think of the best case scenario, the ideal unicorn sort of model that can perfectly split the two classes without making any mistakes. And in this case, the true positive rate for such a model will be 1, and the false positive rate will be 0, because we're not going to have any false negatives. And in this case, we're not going to have any false positives. So, and when we move threshold one way, we're going to be really close to this upper border of this graph, and then changing the threshold in the other way, we're going to be moving this way. So it's going to be really, really hugging that corner. And what we want our model to have is the curve really, really tightly close to that corner. But then again, it's a plot. It's difficult to compare automatically without looking models based on the plot. That's why there is a metric called area under the curve, which basically just calculates the percentage of this plot that's under this curve. When you understand what the curve means and what it does, it's a lot easier to understand this metric. But this is not the only curve that you can use. There is also a precision recall curve, which is, follows exactly the same principle, where you move the threshold and then you plot precision and recall in this case, and then you get a curve and you can calculate the area under it. Again, why there is one curve, why there's another curve. In this case, again, it makes sense to look at the data and see if you have a class imbalance data set. I'm going to use I'll be using exactly the same example. And get the probabilities and plot the curves. And as you can see, for a class imbalance data set, ROC gives 92, and for the precision recall, it's only 57, almost 58. So again, this a lot depends on what kind of data you're dealing with. There's also log loss as another way of assessing the performance of a machine learning model that generates probabilities of as well as predictions. And it also often used as a loss function, of course, and it takes into account uncertainty of model predictions. Here you have y for in binary case is going to be for the true labels if it's a 0, 1, and the logarithm of probability. The minus sign before the formula is to make it a positive number, because logarithm of something smaller than 1 is going to be negative. So it's going to be difficult to compare models with negative numbers. And intuition for log loss is easier to plot than to explain with some words. So if you have a prediction that is, if you have a true label of 1 and predicted probability of class belonging to 1, you're going to have a very small log loss, but the more wrong your predictions are, the more confident your model is in wrong predictions, the log loss is going to skyrocket. So you would care about log loss when you not only care about the accuracy of your predictions, but also about how confident your model is in the predictions it makes. So we've talked about some metrics for binary problems, and let's see how they can be extended to multi-class classification problems. And you can plot the confusion matrix for a multi-class problem. In this case, it's the digits data set, so numbers 0 to 9, actually the handwritten classes, numbers and the classes that they represent. So you're going to have the same story with a true label on in the rows, predicted in the columns. The diagonal is going to be representing the correctly classified examples, but then you can actually diagnose and see like that there's 8 is mistaken for 1, or there's 2 that's mistaken for 3 for some reason, and you can make some adjustments based on what you know about the data. In some cases, something will be expected. In some cases, you can see indication of something's really going wrong with the model. You can also get precision recall and F1 score, but for a multi-class problem, the notions of true positive, true negative, and so on don't really apply directly, but these metrics can actually be extended to a multi-class problem by calculating them per label and then averaging them. And there are more than 3 ways of averaging, but I find that the more commonly used are the macro averaging, micro averaging, and weighted averaging. I'm going to show an example of how they're calculated for precision, for instance, because the other metrics use the same way of the same principle, how the average is calculated. So we're going to take this to example. and we're going to make a confusion matrix, and then we're going to calculate each metric for each label, for each class. I'm going to say we're going to treat them as one versus all problem, meaning that if it's, for example, for a bird that we're going to calculate the true positives for a bird. It's going to be this cell. This is where we said it was a bird, and it was a bird. That false positives are going to be where we said it was a bird, so we predicted it was a bird, so this column right under, but it was not. We're going to sum these up, and this will be false negatives, where it was actually a bird, but we said there wasn't. So we're going to do the same thing for all classes, and then we're going to calculate the totals as well. Now, to get the macro, and weighted average, which is going to add the number of samples here as a column, and micro precision is going to be calculated by just using the total numbers. In this manner, every sample equally contributes to the average, and they equally represent, each sample is equally represented in the average. And then for a macro precision, we're going to calculate the precision per class. Just, for example, for a bird, it's going to be 1 divided by 1 plus 1. It's 1. For cat, 4 divided by 4 plus 1 is 0.8. And we're just going to take the average of that column. And this way, every class, regardless of its size, is going to contribute equally to macro precision. And weighted precision is similar. We're going to, again, take precision calculated per class, but then we're going to weight it by the number of samples about how they are represented in the data. So just micro average, like I said before, it allows you to make sure that all samples equally contribute to the average. And macro average allows all classes to equally contribute to the average, while weighted average weights each class's contribution to the average. And when would you want what? Well, that largely depends on your data, and again, a bit on the business problem. If you have class imbalance data and you have one class that is underrepresented, but you really want to get this one right, you maybe want to use macro average to make sure this class's contribution is amplified and it's on the same level as for other classes. Scikit-learn documentation recommends using micro average for a multi-label problem. I personally haven't done much with multi-label problems, but I'll trust them on this. And a multi-class log loss is actually a more general case of a binary log loss. And the intuition is exactly the same, and the formula looks a little bit different. It's a general case. But it's essentially the sum of, we're going to go through every sample and through every possible label, and for every time we're going to be taking y, which is whether this label is correct for this sample, a binary indicator, and we're going to multiply it by the logarithm of probability of this label being right for this sample. To me, it makes it easy to understand a metric like this to just try to code it. And in my case, I just used for loops to show, to make it more intuitive. But of course, in scikit-learn, it's done with vectorized operation. It's a little more optimized, let's say. So, but for me, it helps to understand it this way. Now, I'm going to switch to regression metrics. And I find that regression metrics are a little bit easier because you're not dealing with probabilities, and you only have a continuous value, and you're predicting a continuous value. You subtract one from the other, you get residuals. And now the question is how to evaluate a model based on all those individual residuals. And if you remember, for all classifiers, scikit-learn gives you a default evaluation metric of which is accuracy, and for regressors, this would be R², also called coefficient of determination. The same way as you would get accuracy with the score method, you can get the R² with a score method for regressors. R² shows you how well model predictions approximate the true values, and it's going to be 1 for a perfect fit, and it's going to be 0 for a dummy regressor predicting average. And why is that? So this actually stems from the formula, and at the numerator, in the numerator here we have the sum of squared residuals, so the difference between the actual and the predicted value, and then the denominator we have the squared distance from the actual values and the mean. And if you think of it, if you have a model that just predicts the mean, the top and the bottom parts are going to be exactly the same. So this will be 1 minus 1 is going to be 0. And if your model is doing even slightly better than predicting the average, then you're going to have the shorter distance between the actual values and the prediction values compared to the distance between the actuals and the mean. And this will be somewhat closer to, the whole metric is going to be somewhat closer to 1. But you can, of course, go negative if you predict infinity for everything is going to be 1 minus infinity, and technically it can be negative, but that means that something is very, very wrong with the model. And the good thing about this metric is that it has an intuitive scale. It's kind of like accuracy, so you get the percentage value, and doesn't depend on your target units, which can be a good thing. But it also doesn't give you any information about the prediction error, how far actually your predictions are from the actuals. And there's a lot of metrics which give you exactly that, because oftentimes you care about the error that a model is making. And the most intuitive one is the mean absolute error. It's basically the average of absolute value of the residuals. And you can get it again as in scikit-learn from dot metrics. There's another way of summarizing this, getting the average of the residuals using, instead of absolute values, squared values, but then you lose the metric is now not in the units of the target value, but it's instead in the squared units of the target value. That's why more commonly you would see RMSE being used, which is basically just a root of the mean squared error. And mean absolute error and root mean squared error have a lot in common. They range from 0 to infinity, and they have the same units as y values, so you can see the error that your model is making in the units of the target values. They don't care about the direction of the errors because of the values of residuals are just squared or taken or have the absolute value. And you want this metric to be as low as possible. But they're different, of course. And RMSE gives very relatively high weight to large errors, because the residuals are squared before contributing to the average. And this makes absolute error more robust to outliers, because because they're not squared. RMSE is often used as a loss function because it's differentiable, but for an evaluation metric it doesn't matter this much. And there's a lot of debate, and you're going to see a lot of tutorials saying, no, you should use mean absolute error of not RMSE for evaluating your metric, because RMSE isn't appropriate, and it misinterprets the error. And these articles are mainly based on the paper that was published in 2005 by Wilmot and Matsura, However, a bit later in 2009, there was another paper by Chai and Draxler that argued that actually it's not the case, and then RMSE is perfectly fine metric, and in fact, and sometimes can be better than the absolute error, especially if you expect the error distribution to be Gaussian, which is often the case. And it's important to know that neither of this metric is going to be good enough on a small test set when you have less than 100 examples. But in practice, most of the time, you're going to have more examples in the test set, so that's okay. And in practice, I find that RMSE is a completely fine metric to use. And if you really, really want to downplay the outliers, you can use mean absolute error to as a second metric but for most cases, RMSE seems to be doing well. And there's one version of it which also is quite often used. It's a root mean squared logarithmic error, which is very similar to RMSE, except instead of y's, you get a logarithm of y. And there's a small technicality as why there is +1. And the good thing about this metric is that it shows relative error, and this is important in cases where your targets have an exponential growth. For example, if you're predicting prices and they have a wide range, if you want to error of $5 for $50 be quite a large error, whereas you wanna, if it's a $5 error on a $50,000 price, it's not a big deal. So logarithm helps you to level these things. It has an interesting side effect. It also penalizes under-predicted estimates more than over-predicted, which is also sometimes useful. So I've rushed through a lot of metrics, both for classification problems and for logarithmic problems, regression problems. And I don't expect you to fully understand them all, but what I want you to take away from this talk is that there is a reason for this variety. And there is no metric that's going to fit all the cases. You need to get to know your data. You need to understand how many outliers do you have, if it's a class imbalance data or it's not. Without understanding your data, your metric may not make sense. And more importantly, you have to know your business problem and understand what your model should care more about, because in some cases, one metric is going to help you more to achieve your final goal. In some cases, it's going to be another. So you always need to start with knowing your data and knowing your problem. Thank you. I've put some
Okay, guys, we are done with the topics, and we are done with the topics, and we will start in 5 minutes talking about final presentation, final exam, and final project report. So I'll pause here. I'll give you 5 minutes break. Then please come back. What is it now? 9:44 at 9:50. If you need to run to the washroom, drink something, At 9:50, we'll meet in order to talk about all what is remaining till the end of the term. See you in a bit. Okay, guys, welcome back. I will share my screen. So, guys, final project presentation to be uploaded here by one member of each group. This would be end on July 26th, which is next Monday after the presentation at 10 p.m. So don't forget to upload your presentation. And for the presentation, I put a template. Your presentation should not exceed 15 minutes for the whole group, and we will allow 5 to 6 minutes for questions. Is that clear? Then final report, final project report, it is due on August 1st at 11:55 p.m. So it is due on August 1st, which means Monday before the midnight. So one member per group will submit the report. Here, if you press, there is a guide. So introduction, problem definition and motivation, related work, methodology, results and discussion, conclusion, referencing. These are important points to mark your report. Proper use of reference and proper citation according to IEEE format is a must. Proper citation is required. What do you mean by proper citation? In your progress report, some students, they write a paragraph without citation in the introduction. This would not be acceptable. So you have to see how papers do proper citation. One member of the group should submit the report in OWL. Final submission should include the final report and all associated Python codes in zip folder. Final report name, group number, these are the format. So it should not exceed 10 pages in maximum, and one cover page, which is 11 pages, including references. And it's Times New Roman, single space, 12-point font size. Okay. And using IEEE research paper format, and the research paper format, sorry, it's not 12, based on IEEE paper template. If you look here, it's giving you how to fill the name. This is for the abstract. These are for the introduction. So you have to follow and keep the same format. And it's giving you for the equation, for the figures, for everything. So this template is a full detailed template. So maximum, then you will add the cover page that I gave to you before. So in total, it should not exceed 10 pages for the paper and 1 page for the cover, 11 pages. But if you have like 8, 7, 6, and you fulfill the topic in a good manner, I don't mind. But as maximum, 10 with references. Questions till here. And here you can submit your code. In this area, you can submit your project code. Any question till here? No, it's in person with no exception for all group members. All groups, all students should attend next week at 8:30 in our designated classroom. I will send an announcement. The TA, Afshan, with our thankfulness for him, will make sure that the room is ready. I will attend via Zoom and Afshan will attend in person. Clear, roping? And this, we said this from the beginning of the term. You are welcome. That no exception for final exam to be in person and no exception for final project presentation to be in person. This is mentioned in the course outlines from the first class. Any other questions, guys, before we start talking about final exam? Everything is clear? Seems no questions. Okay. For the resources, how to study to the final exam. The final exam, I made my mind that we will have 40 questions. Each will weight 1 point. You have 3 hours to answer the 40 questions. All the questions will be multiple choice, true and false. I'll not bring mathematical proof or mathematical derivatives to make it easier for you guys. How to study? You have the handout. You have Andrew and G videos, our class recording in the YouTube. Any source you find it's good, it would help you in the machine learning section and courses, all almost the same, all universities all around the world. What I will do tomorrow or after tomorrow, I will try to make categories like handouts and videos. Is that clear? And look, now next Tuesday will be our final project presentation. It's a big milestone in our project. August 1st, you will submit your final report with all associated code. Okay? Make sure not to copy and paste. You did very well on the progress report. Some groups, they have high percentage of copy and paste. I wish that in the final project or in the term paper, there is fewer percentage or less percentage on copy and paste. In August 2nd, I will release a document in the resources. You will receive an email about that, which is like final exam preparation questions. So you will have like 3 to 4, maybe 5 multiple choices, and also 4 or 5 true and false for you to get like familiar with the questions. August 6th, I will post the question answers. So try in between to study and answer those questions by yourself, then match the question with the solution, your answers with the key solution. So this would help you to study well for the final exam. Yes, Chandan, there's no question on mathematical proof or derivative and no calculations, but sometimes you might receive a question in multiple choice. But no, I will not go deep in math. in the exam. I'll not go deep in math in the exam. I'll like test your understanding. But you'll not do any, you might use your calculator for, no need for calculator, I believe. In certain question, if there's a kind of calculation or numbers, like for example, if we have this false positive, this false negative, true positive, true negative, give me the precision, for example. Give me the accuracy. Like these are simple calculations. So Afshan, allow them to use calculators. Okay, Afshan?
Yeah, sure, okay.
So on the final exam day, allow them to use calculators. I might bring some question about F1 score, precision, but it will be in the choices. It will be in the choices. So you just do your equation, then you will find the number. But other than that, I don't believe that you need a calculator or to calculate anything. Any other question? Thank you, Chandan, for this question. It helps all of students. Any other question about the final exam, guys? I'm sure most of you will be done. I start to put the skeleton of the exam. I'm sure most of you, if you study well, it will not take more than an hour and a half to 1 hour 45 minutes. But you have 3 hours. If you don't have question, guys, you are free to leave. I will upload this recording right away after the class once the computer finishes the recording. If you have a question, please stay. It was a nice turn. Oh, I believe, guys, wait, hold on. I believe that they sent me an email today to ask you to do this course evaluation, the feedback from the university. So they always ask us to encourage a student to do it. So please feel free to fill it once you have time. Thank you, guys. Thank you. Thank you, everybody. Thank you. Thank you. Thank you. It was a nice term with you guys, but we still have like some few meetings before the end of the term. Thank you. Thank you. Thank you, everybody. Thank you. Louis, do you have any question? Rambo, do you have any question? I'll stop recording right here. Thank you, guys, and see you next week in the presentation.